let's get started. Welcome, everyone. Like I said, this is the Quantum Materials Qubo webinar, the foundations of quantum technologies. Hello, my name is Dr. Katanya Kuntz. I'm founder and CEO of Qubo Consulting Corp, where we are helping make quantum accessible for you. And today we have a special guest speaker who I'll introduce in just a second from Applied Quantum Materials. And so we're very excited because we have a founder who has a company that's based on quantum materials. So who better to educate us today than him? So hello again. My name again, Dr. Katanya Kuntz. I'm an experimental quantum physicist. If you're not sure what that means, I have a slide coming up showing what types of experiments I've done in my career. So Qubo Consulting, we're offering quantum training and advising for both technical and executive audiences. I myself, I'm a technical translator, advisor, and an industry connector to this global quantum ecosystem. And this is one of the experiments that I did when I was in my undergrad at the University of Calgary. I actually made a lightsaber right there, that beam in the middle here. You can see it looks the same size, the same width, the same brightness, and then all of a sudden it just disappears, just disappears into nothing. So this is a special type of light beam called a Bessel beam. And so the whole point of this experiment was to create this special beam of light. And I think it looks like a lightsaber, so that's pretty cool. But these are the types of experiments that I work on in my career, in my research life. So we have lasers, we have optics, we have various electronics, things like this. So this is the type of thing when I say experimental quantum optics, we do this type of thing. All right. And now I'd love to bring onto the stage Lorna. Unfortunately, you won't see her face unless you go to the other tab, to the meeting tab and see the gallery. But this is what Lorna looks like. And she's going to welcome you as well. So Lorna, take it away.
Hi, everyone. Welcome. As you know, we're really excited to have you here for our quantum materials. I just want to remind you, the session is as good as you make it for yourself. So the more interactive you are, the better. So please keep an open mind. We are going to talk about quantum physics, but I promise you that you'll understand it. If I can understand it, you guys can understand it. Yes, ask lots of questions. The best way to learn is through your own questions. I think here we don't have a Q&A box, but there's tons of us here who are monitoring the chat, and we will make sure that we get to your questions. If not, feel free to raise your hand. I know when Dr. Katanya is speaking, she prefers that you ask the question while she's going through the material rather than waiting till later on. So feel free to, raise your hand, interrupt, and we'll make sure that we get to you. And there will be lots of time to ask questions at the end as well too. So again, just like how she said earlier, make sure that your Zoom name matches your registered name. The buck stops with me here. I'm doing the final attendance. So just please make sure it's more helpful for me that you have both your first name and your last name up. And I hope you guys enjoy.
Amazing. Thank you very much, Lorna. All right. So today, as I said, we're going to talk about quantum materials. So I'm going to give a brief introduction into what are quantum materials, how do they connect to different quantum technologies. We're going to do a quick little deep dive, not too technical, but I'm still calling it a quantum rabbit hole because I think it's cute. So we're going to do a quantum rabbit hole into what is superconductivity, absolute zero, and also the topic of the Nobel Prize in Physics from last year in 2025, quantum tunneling. These are all connected to these fancy materials that act weird if, for example, we supercool them. And so, yeah, we're going to talk about that. And then we're going to bring on our guest speaker, Dr. David Antonuk, the co-founder from Applied Quantum Materials. All right. So, and as Lorna said, happy to take lots of questions. please put them in the chat. We don't have a Q&A box. We figured this out now. There is no Q&A box. But luckily, there's not too many of you on the call, so we're definitely going to be able to see all of your messages. And we'll have some spots for Q&A as well if you want to unmute and even come on camera and ask your questions that way too. All right, so starting off with, what are quantum materials? Well, let's take a step back. What is quantum? So quantum is referring to quantum physics. This is the physics of the tiny. And sometimes it's called quantum mechanics. That's the mathematics behind the physics. And so this is the study of the smallest particles and energy that make up our universe. Things like atoms, ions, photons, which are particles of light. These are things that you can't see with your naked eye. They're smaller than what we can see, even smaller than the things you can see with some microscopes. And so on this tiny scale, the world just behaves very, very, very differently compared to our big everyday macro world. And you might not know, but you already have quantum technologies in your life right now. The fact that we're having this conversation using the internet and using computers and the microchip, those are all devices that operate on the principles of quantum physics, but they're not necessarily the next generation of quantum technologies that we're going to talk about today. Other forms of 1.0 technologies would be like X-rays. That's using a different part of the light spectrum to examine your body. Also electronic displays. Liquid crystal displays and LEDs, light emitting diodes, used in a lot of your TV screens and phone screens. Also GPS. So if you've ever used Google Maps, you've actually used an atomic clock, and that's a form of a quantum technology. So what are these 2.0 technologies? So now when we start to use individual particles to do the computing, the sensing, the communication, even designing new materials at the quantum level, right? This is where we're crossing into the second revolution. And so things like atoms, trapped ions, superconducting circuits, we'll hear about that more soon, and photons. These are all things that we can use to do these operations, and they're called quantum 2.0 technologies. And so now, what are quantum materials? Quantum materials refers to materials whose useful properties arise from quantum effects that have no classical explanation, and often from a collective behavior, a group behavior of many particles acting like one. Some examples of quantum materials you might have heard of before, superconductors. That is a quantum material, and this is a picture of a type of superconductor that's used as a quantum sensor, designed by a Canadian company, Qubo Technologies, used for, again, quantum sensing. Here's another device made by Phaser Quantum, and this is a portable nitrogen vacancy diamond quantum magnetometer. And so this device does very, very precise magnetic field measurements. And so this is also, this diamond and this nitrogen vacancy center device, that is a form of a quantum material. So what about quantum computers? Are they connected to these quantum materials? Definitely. So if you were to just do a search, what is a quantum computer? Often an image search would bring up pictures like this. And lots of people think that this huge chandelier looking thing that's like half the size of a human sometimes is a quantum computer. But actually, that is the cryogenic fridge. The actual quantum computer is a superconducting circuit, this chip here. So for example, this is a D-wave chip. And so for something to act in its superconducting state, it has to be very, very, very cold. Almost what's called absolute zero. And I'll explain that in just a second. So this cryogenic fridge and all these different stages here, these different layers that you see with the gold plates here, that's to bring the temperature down. And at the very, very, very bottom is where the temperature is almost absolute zero. It's just above the absence of any temperature, any energy at all. It's incredibly cold. And so in order to make this superconducting circuit, which is a quantum computer, in order for it to function, it has to be very, very cold. And so that's actually the computer is this chip. It's not the fridge. And so this is a form of a quantum material, this superconducting circuit. And so like I said, let's talk about what is absolute zero, just as a high level perspective in relative to other things you might know about or hear about. So this quantum rabbit hole. So again, we're trying to go all the way down here. If we have this thermometer here to absolute, almost at absolute zero. And so this Kelvin scale, which is what the K stands for, right? And so this relates to our everyday temperature scale. Like if you live in some countries that use Celsius, like Canada. So Celsius, so 0 degrees Kelvin is the same as minus 273.15 degrees Celsius. So incredibly, incredibly cold. But like, how do I put that into perspective, right? So I know water way up here, water freezes at 0 degrees Celsius. And 0 degrees Celsius, yeah, I know, we got a little bit of math here. Just hang on. 0 degrees Celsius is the same as positive 273.15 Kelvin, okay? So if I know ice is up here, and I know this superconducting circuit thing is way down here, how cold is that? Okay, well, liquid mercury freezes to solid at minus 38 degrees Celsius. So there are some thermometers that would stop working in my backyard in the middle of winter. Also, even colder, the temperature on Mars. So the average temperature on Mars is minus 65 degrees Celsius. Still a lot warmer than a superconducting circuit. Okay, another planet. The temperature on Saturn is at minus 140. What about the boiling point of liquid nitrogen? If you've ever been to the Science Center or to a cool drink mixing bar where they use liquid nitrogen to make your drink look all misty and foggy, that is at minus 196 degrees Celsius. We're still nowhere close to this 273. So this means the superconducting circuit is even colder than liquid nitrogen. The temperature on Neptune is even colder than that. It's at minus 200. And then we have the background of outer space. So the temperature of outer space, or what's called cosmic background radiation. So what this picture is showing here is like a heat map of the universe. If you take a slice of the universe and you look at that, the dark, dark, dark parts, these aren't stars. These are the dark, dark, dark parts. And it's not uniform. It's actually got this pixelated nature to it. And the average temperature is around 2.725 degrees Kelvin. So that's minus 270.42 degrees Celsius. So now the background of outer space is almost 3 degrees Kelvin. So these superconducting circuits are colder than outer space on planet Earth. I think that's just mind-blowing that we do this every day. All right, so we're going to pop back out of our rabbit hole. That is how cold absolute zero is. And like I said, quantum computers use all different types of quantum materials. We've been focused just now on superconducting circuits. As you see in this highlighted box here, tons of companies that have various devices that based off of these superconducting circuits, including IBM and D-Wave and Google and Rigetti. But look at all these other platforms. You've got neutral atoms, the NV diamond centers I was talking about, topological qubits, even the photonic quantum computers, the ones that use light, they're using quantum materials to do the measurement of the light. We will use superconducting nanowire single photon detectors which is again another form of a superconducting circuit. So it has to be super cooled down to cryogenic cold temperatures, like just above absolute zero. Some of those devices can maybe operate at like 1 degree Kelvin. It doesn't have to be at 0.0001, but it's still cold. And so these photonic devices, they involve quantum materials. Cool. So let's check in now and see if we have any questions yet. Let me pause my sharing for a second. Hello, beautiful people. How are we doing? Did I blow some minds? Did you know all that? I don't see any questions yet. I think we're still good.
We're still good.
Okay, awesome. All right, let's go back in. We have one more quick rabbit hole to dive down, and then we will bring our guest speaker. All right, the Nobel Prize in Physics from last year, 2025. How does this all relate? So the Nobel Prize in Physics in 2025 was awarded to John Clark, Michael Dvorak, and John Martinez for the discovery of macroscopic quantum mechanical tunneling. We'll explain what that is, and energy quantization in an electric circuit. So basically, they created a big thing, an electric circuit that you could see with your eyes and you could touch with your fingers, and it was like a full centimeter in length. That electric circuit showed quantum effects. So they combined the quantum world with a macro big world, and that is a big deal, and hence a Nobel Prize, and all the quantum technologies that came out of this. So this cartoon is from the Nobel Prize Committee, and I think it does a nice way of explaining this quantum tunneling. Sometimes when I mention quantum tunneling, I say it's as if your neighbor, instead of knocking on the front door, just walks through your wall to come say hi, right? So in the macro world, in the big world, everyday world, if you throw a ball against a wall, it will just bounce back at you, right? It doesn't go through the wall like this other picture looks, right? But in the quantum world, particles can do stuff like this. And so in quantum mechanics, this phenomenon is called quantum tunneling. And it's very bizarre, and it happens in everyday life, which I'll go through in just a second. So the official definition of quantum tunneling is that a particle is able to travel through what's called a potential barrier, basically like a wall. You could think of it like a wall. Even if the particle doesn't have enough energy to do that classically. So classically in the classical physics, the physics of the big, Newtonian physics, versus quantum. And so classically, that particle doesn't have enough energy to do what it's apparently doing. And so when this happens, it can be referred to as quantum tunneling. So this is actually in our world, like right now. So there's tons of things in nature and in our technology, both classical and quantum technology, that operate because quantum tunneling is real. Did you know that quantum tunneling is necessary for nuclear fusion to occur in stars like our sun? I didn't know this until I learned this. So it turns out that the temperature and the pressure in our sun, in our star, is too low to classically explain how two protons, the two positive particles in a helium atom, how those two protons can overcome what's called Coulomb repulsion and form a helium nucleus. So the fact that nuclear fusion is happening in our stars all the time is proof that quantum tunneling, this effect, is real. If it wasn't real, then the protons wouldn't be able to overcome this electrical, because they're both positively charged, so they're going to repulse each other. Think of two magnets. If you take both south poles of magnets and push them together, they repel each other. This is all part of this Coulomb repulsion. And so if you can form helium atoms, if those protons are able to get over that potential barrier that they shouldn't have enough energy to get over, that is proof of quantum tunneling. So go look at the sun and you see it. And they also made this really cool graphic explaining the Nobel Prize in another form. So an everyday conductor, right? So like a wire, something that like a metal wire that conducts electricity. So that type of material, it has some resistance. And so in a normal conductor, the electrons, which are being shown by these little dudes jumping around with little faces, and they're all doing their own thing, right? In a conductor, they're jostling with each other. They're causing resistance. They're not acting in a coherent way at all. But if you super cool certain materials and make it a superconductor, all of a sudden this material has no resistance. It acts as if it has no resistance. So now you see the electrons, they've paired up, and now they've got a buddy, and they're in these Cooper pairs, okay? And so when the electrons transition into this state and they form Cooper pairs, this marks the point where current just flows through the superconductor as if there's no resistance, which makes no sense in the classical world. In the classical world, voltage equals resistance times current. If I have no resistance, that's a zero, and zero times anything is zero, so then there should be no current. But in a superconductor, classical physics doesn't make sense. You have to use quantum physics to explain this phenomenon. But it's real. And then we can use these Josephson junctions shown by this gap here. So this is the potential barrier where the electrons shouldn't be allowed to transition over, but somehow they do. And we can use these devices for example, quantum computing. So like a superconducting circuit is based off of this principle. And so in this final image here, you see that the Cooper pairs, they're all behaving as if they're now one continuous particle. And so remember the definition from the start of when I started talking about this stuff. What defines a quantum material? It's where quantum effects have no classical explanation, check, and often from a collective behavior of many particles. That's what this last part of the cartoon is showing. So these Cooper pairs actually stop acting as individual pairs of particles, and now it's just one continuous wave function, one continuous mathematical expression that explains this state. And this is very, very, very bizarre, but very useful because we can make a lot of quantum devices using that effect. Just like this. So like I said, this superconducting circuit is operating in the same way with the Cooper pairs and Josephson junctions. So the Nobel Prize from 2025 is very applicable to our everyday life right now. All right. So that wraps up my introduction. I just want to check in and see if there's any questions.
Yeah, Giannis had a comment. He said the paranormal people must be losing their minds over the behavior of particles.
I love it. Yeah, there's a lot of spooky things that happen between quantum and other things. Okay, I'm going to stop sharing if there's a few more questions.
There is someone asking if you can explain the coherence.
Yeah. So when I say coherence, that's like a big, there's a lot that goes into that explanation. So I have actually in one of my courses, I think I have like 4 or 5 slides just explaining coherence. But in this instance, right, you can think of it like the electrons, when they're not in the superconducting state, they're very random. They're jostling all over the place. It's very chaotic. And so they're decoherent. They're not coherent. And then when you supercool the material, the electrons start to behave as if they're one particle. Instead of individual particles acting randomly, they now act in like a collective state. And that's why we say they're coherent. Another way to think about coherence is light. So a light bulb, like a regular light bulb, is giving off random, incoherent light. It's going in all different directions. it's at different, slightly different colors, right? It's not all exactly one color. Like an LED is exactly one color. Um, and there's also something called phase. And so phase is very important when you're talking about light, when you're talking about interference, even with particles. And so when things are in phase, then they're coherent. If it's a random phase, then they don't have a phase relationship, then it's called incoherent. And so light from a light bulb is all of that. Whereas light from a laser is coherent, it's one color, it's in phase, it's everything that's not a light bulb. So that's the best way I could explain incoherent and coherent. How's that? Awesome.
Monica made a comment to what you just said. So the properties of superconductors make all materials like copper.
Yeah, yeah, I see what you mean.
Yeah. Samira has a question. How does quantum material affect quantum metrology? Metrology or meteorology?
Oh, sure. Metrology. Yeah, yeah, the measurement. Yeah. So, I mean, David might even talk about that. I might want to hold on to that question. I don't know, but in my opinion, yeah, so you can definitely do like nanotechnologies and things like that for metrology and medicine and healthcare. I'm more familiar with like applying light to do metrology, to do sensing, to do, very precise measurements. But I don't know. David, do you have any?
We'll talk a little bit about this in the presentation about applications.
Okay, perfect. So let's maybe hold that question for after David's presentation. Awesome. All right. So if there's anyone else?
No, that looks like that's it in the chat.
Okay. All right. Well, like I said, that was a taste to get us started on what is quantum material. And now let's bring on our guest speaker. So let's pretend we don't know who it is. So today we have a quantum tech founder who will share about their company and quantum applications. Welcome! Dr. David Antonuk is the co-founder of Applied Quantum Materials. It's an Edmonton-based deep tech company developing next-generation quantum materials. David holds a PhD in engineering physics from the University of Alberta and brings over 30 years of business and product development, technology commercialization, and building strategic business relationships. Applied Quantum Materials has become a global leader in silicon quantum dots and nanomaterials. The company's materials are being integrated into quantum computing, silicon photonics, quantum sensing, nanolithography, and life sciences applications. Welcome, David.
All right, thank you very much.
You're very welcome. I'm going to stop sharing.
Okay.
Take it out and take it
All
over.
right. So, AQM, we're actually a little over 10 years old. We've been developing quantum materials during this time and applying it to many different applications. And so my talk today will be a little bit about where we see what we've done, where we are, and where we're going in terms of these quantum materials. And we feel that it's kind of like the foundation of like the next industrial revolution. There we go. So we are, like I said, we're an ISO 9001 company, 10 years in operations. We're active in 30 countries, lots of customers, distributors around the world. We develop these novel materials and solutions to transform different industries. Here's an example of some of the companies that we work with. I mean, so you see national labs around the world, you see large multinational corporations in memory system, telecom, quantum, defense related. We even have some in automotives, and AGC is the world's largest glass company. that we make materials for some application that we have an idea what they're up to and things like that. So we work with universities, national labs, lots of startup companies, and multinational corporations. So our nanomaterials, I'll go through a little bit about what we actually make. So the first one is the silicon nanoparticles, which are silicon, silica, silicon, and silicone. They're doped. We can use them for medical imaging, diagnostics, etc. I'll go a little bit more into that. So what you're seeing there are different colors of the rainbow. Those are quantum dots. So those quantum dots are between 2 and about 7, 8 nanometers in size. So each of those colors represents a particular size or a functional group attached to it. To develop at that precise areas requires extreme precision in terms of we're making, say, 3 nanometer materials that are plus or minus 10%. That's how precise we need to make these things to get those sort of colors and vibrancy. So one of our starter materials is a silicone polymer. We use these as photoresist for electron beam lithography, nano imprint lithography, EUV lithography. We can range feature sizes are less than 7 nanometers to 2 micron feature sizes. Applications are in quantum integrated photonic circuits, and we're moving into 2-photon polymerizations, so 3-dimensional structures now. We can take these materials and we can incorporate them into different polymers to create these nanopolymer materials. So we create optical films and coatings. Something new that we've recently come up with is a PFAS-free. So PFAS is Teflon, bad for the environment, forever chemical, etc. These coatings can be applied onto polymers, glass, silicon, and they essentially are durable water repellent and oil repellent. So what you're seeing, that little blue dot is a water, and that little pink dot is oil. And we've coated a polyester fabric, and nothing sticks to it. So it actually repels these different things and different solutions and liquids and things like that. And it has very interesting applications for replacing the PFAS Teflon coatings that you have in the apparel and sportswear. So we also have the ability to make all kinds of metal, non-medical nanoparticles, all different types of materials, carbon materials, graphene oxide. That little Y shape that you see there, that is actually a biomaterial that has been coated with metal nanoparticles to provide both conductivity and antibacterial properties. So you can do this, once you understand the materials, you can do these things, and you can apply these materials to create completely new structures, completely new materials, completely new polymers, etc. And a little bit lastly is one of the side projects we've been working on is to create a solid-state aluminum-ion battery. We're the first in Canada to make this a solid-state battery. It has double the specific capacity of lithium-ion batteries, and it's air and thermally stable, 4 times the volumetric capacity, 100% recyclable. It's just 4 layers put together. You understand the materials, you put it together, you have a battery. There's still work to be done on the cyclability, etc., on this battery, but we've got an amazing first step in terms of this battery. And totally safe material. So here's an example of some of the silica nano and microparticles. So these materials are, we can tailor their crystallinity, whether they're crystalline, amorphous, mesoporous. We can change their size anywhere from 20 nanometers to over a micron in size. And then we can surface functionalize these things to give you pretty much any property that you want. like hydrophobic, oliphobic, conductive, antibacterial, fire-resistant, antibacterial. So as an example, what you see is we have these materials. We can add dyes, chemicals, some other materials to create just about what any company desires for enhancing their product. So the image below shows these dye-doped materials that we can put chemicals, drugs, just about anything you can think of. We have the ability. So our expertise really is in manufacturing the materials as well as the surface functionalization and adding the appropriate modifications. And if there's any questions, just feel free to kind of interrupt.
So far, there's a comment. Talk about an industrial revolution.
Yes. So I'll get into a little bit of the electronic materials that we do, which is kind of getting into some of the work that we do. So here's some work on the lithography side. So you see, traces, features, dots. We can make structures. The one on the far right, that is materials that we've sent over to another local company called Applied Nano Tools. They're making Fresnel lenses and for X-ray optics. So again, that gets into the metrology. How do you make a X-ray microscope? Well, you need these materials to give you the proper lenses to make this particular type of system. So currently, we make it's called, this HSQ photoresist. We're a global manufacturer. We've been making this now for about 8-9 years. We've been developing new photoresists. So photoresist is simply a material that reacts under photons, or it could be electrons, or it could be various different ions, or even lasers. So we can adjust the consistency of the materials so that we can use it for various other applications, such as two-photon polymerization and volumetric additive manufacturing. So we're getting clients now to do this. One of the things that we see is that because we're material specialists, people come to us with problems, and they're developing and designing something new. So we see that ahead of everybody else who's before commercialization. So our materials help to build these photonic and optoelectronic devices because we can manipulate the light matter interactions with these things. And again, so we can make different kinds of quantum devices for quantum computing, resonators, masks, silicon-based photonic circuits, spin-on glass, and conformal coatings. And I'll talk a little bit about some of those things, what they mean a little bit later. So here's an example of this amphiphilic coating I mentioned before, so water and oil. So it's PFAS-free. We use a hierarchical micro and nano structure, and we actually dip the cloth into the structure. It's completely invisible. You do not see it. These materials are completely non-hazardous, not like Teflon. And the coating's been applied so far to polyester, nylon, silicon, glass materials. So it completely is repellent to these various different surfaces and stuff. Although ketchup and mayonnaise are a little bit of a problem too because they're thick, but we're still working on that one. So you can see what happens on with an SEM. You see the fibers, but we've not coated everything. We've only covalently bonded the actual nanostructure materials directly to the polymer fibers themselves to create this effect. So what that does is it allows breathability with the fibers. So your shirt, your clothing still breathes and stuff like that. Our competitors out there, they just coat everything in polyurethane, which makes it feel like you're in a rubber suit and it doesn't breathe, etc. So applications, textiles, displays, optics, biomedical, protective coatings, etc. So these are the examples of using these nanomaterials for. So an example of quantum-based sensing. So here we have a quantum dot, the yellow dot there, and then we can use different techniques such as electron transfer, fluorescent resonance energy transfer, and photocurrent generation for sensing applications. Again, there's your metrology application. So by using these quantum dots in different applications, you can create and measure things. Okay, so here's an example. We use quantum dots as explosive sensors. In this particular case, what you're seeing is a blank piece of paper coated with quantum dots. You apply various different kinds of explosive materials. We can get detection limits of 10 nanograms. And how this works is that the silicon quantum dot, when it's exposed to UV light, well, the electron goes from the valence to the conductive band, and it re-emits another light. But when it's in contact with nitroaromatics, like explosives, what happens, it quenches it. It does not emit. So that's why the images where it's been touched with the explosive material turns dark. We've shown that we've been working with RCMP and et cetera. You just touch the surfaces with the paper and you can detect it. Now, if you can do this, you can look at various different types of pathogens. You could look at biogenic amines, food pathogens, et cetera. You can use the same technology for all of these things. So now I'm going to look a little bit translating these quantum dots into bio applications. So we take the quantum dot and then we functionalize it with all kinds of different biomolecules, like antibodies, drugs, et cetera. And then we can create all kinds of new applications, such as diagnostics from bioimaging, biosensors, labs on a chip, doing personalized medicine, regenerative medicine, tissue engineering, drug development and delivery and therapeutics. So all of these things can be done by understanding the materials, functionalize the materials, and then create new types of technologies. So this is just the first step into a whole new area of nanomedicine that is being created, and using quantum dots and other types of nanomaterials that we can able to do all of that sort of stuff. Now let's go back into the quantum hardware. I mean, Katanya introduced a little bit of this stuff. So you have superconducting, trapped ion, quantum dot, photonic, and neutral atom. So AQM is currently working in the top four, those four. So we're actually working with clients in those areas to provide them with the materials for this. And we'll be we're doing a proposal on the fifth one, the neutral atom one, with a company or organization in the near future. So the problem with the quantum hardware and the qubits are material defects. You have stray noise, you have photons running around, you've got magnetic field fluctuations, lasers doing all kinds of things like this. So in order to solve the problems, you need to have materials that are can increase and improve the coherence times of these quantum qubits. So the one of the things that we found is that having the processes and materials compatible with standard chip manufacturing is really important. It shortens the time frame to get these products to market. So all of these things have to be designed in collaboration with the companies that are manufacturing these things. I was in Korea a few weeks ago at Quantum Korea, and IBM had their Kookaburra chandelier there. And I'm talking to the researcher, and I'm going, so that little box right there at the very, very bottom, it's cooled to 0.001 Kelvin and stuff like that. That's where our materials are, right inside that little box. And then next door was IonQ. So you're looking at and seeing their trapped ion system, and our materials are somewhere in their system. So the material needs for qubit manufacturing. So we need materials that are ultra high purity, low microwave loss, even at these cryogenic temperatures, and isotopic purification. So it has to be very pure. the superconducting films, as we mentioned, the ultra pure aluminum, niobium, tantalum requires these clean interfaces, no defects to prevent the energy loss in the circuits. Again, on the silicon spin qubits, you have to have ultra refined pure silicon 28 to eliminate that nuclear spin noise. Low loss dielectrics, aluminum oxide, titanium nitride. These are materials that are used for these tunnel effects, resonators, and must exhibit near zero dielectric losses so that the signals can be not lost in the noise. And again, we were talking about diamond and silicon carbide, using those crystal synthesis to control those vacancy placements. So this is going to be a long slide here, but this is what we're working on right now, quantum materials for photonic and optoelectronic devices. So we are working on these various different areas, but the first one is that we're providing materials for organizations, groups to do these QPICs. So silicon waveguides, micro optics, and all of this sort of stuff. So building these photonic crystals to control the flow of light. We're selling materials for people that are using single photon sources and detectors to make these superconducting nanowire single photon detectors. There's one company that we're selling materials to. So these materials are used for like the purity for the quantum dots and things like that are to get the high efficiency OLEDs, displays, color purity, all of these things that sometimes you watch your TV. This is the technologies that are being used for this. I mentioned diffractive X-ray lenses, Fresnel zone plates by the local company Applied Nanotools, micro superconductors and nano electromechanical systems, 3D printed networks to store energies, etc. Three-dimensional metastructures. This is a new area for us that we're working on to develop these polymetric resins to create these new structures, 3D structures by stereolithography, two-photon polymerization, and volumetric additive manufacturing. One of the things, because these materials are essentially inorganic silicon or silica, they're like glass, so they're chemically resistant, can withstand very high temperatures, and we can get feature sizes as low as 20 nanometers with these structures. And kind of like our bread and butter here is this ultra high resolution lithography. So we can make these various different materials for the lithography industry, and they can make their transistors and optoelectronic devices. One of the things that our HSQ material is used for is like a spin-on glass. It's a low dielectric constant. We coat various different circuitries to protect them. So we protect them, and we allow reduced transition capacitance through the layers on the chips so that we can get faster signal processing. And lastly, we can make thin film protection again to because our materials cure at low temperatures. We can use that, and it just doesn't destroy the circuitry and other delicate components that are in some of these devices and stuff like that. So quantum material challenges. Okay, scalability in manufacturing. It's a big problem. To create high yield fabrication on CMOS platforms, major problems. Heterostructural integration. We're combining all kinds of different materials together on a silicon substrate to maintain this chip functionality is another challenge. Material quality, defect-free, monodispersibility of these materials so that these materials are always the same, they're exactly the same size, they perform in exactly the same way. And lastly, one of the issues that we haven't run into a little bit, we're starting on the medical side, is regulatory safety. The uniqueness of the materials, there is no standards, and industry has to work with government agencies and industry associations to make sure that standards are managed. So next steps. So this is kind of where we're going. This is kind of the wrap up. So photopolymerization is a brand new area that is looking at complex 3D microstructures, metasurfaces, waveguides, and stereolithography devices. So we can actually build devices not from traditional lithography, but actually build it in 3 dimensions. Incorporating our quantum dots into these printed architectures enable us to combine functional, the light matter interactions, photonic devices, essentially. This gets us, now we get ourselves into a lot of the bio side where we're doing fluorescent cell scaffolding, biosensors, lab on a chips, etc. So you're seeing this, it's exploding into all kinds of different applications now. And sort of lastly, so industry, from our perspective, what they're looking for is a fast prototyping solutions, low cost for direct write systems. So we're aiming to lower that threshold for researchers, companies to enter into these new diverse areas, and both with the materials, fabrication processes, and tools to create these new quantum building blocks. Okay, that's it. One last thing. Yeah, what we're looking for. So market activities and partnerships. So in order for us to do this, we're looking for co-development partners and end users. So these are examples of what we can use with. Here's examples of some of the things that we've been working on. And we're looking for companies to work with, and that we can make new devices, new systems, and we can sell more products. I guess that's where we are.
Dr. Antonik, there is a person who is asking, Mariana. She's wondering where your manufacturing facilities are located and if it would be possible to visit.
Yes, we're in Edmonton, the Research Park.
Okay. You got that, Mariana? Edmonton, Alberta. I think I see my colleague here, Marco, with his hand up. Marco?
Hi, thank you. Very interesting. I was wondering, I heard that you can approximate the resistance with a series of Josephson junctions and you save a lot of space. Is this something that is actually implemented in practice?
Yes. So one of our clients, IBM, actually uses our materials to make 10 nanometer widths. Those are the gaps, or 10 nanometers. I've actually seen it. The work that they've been doing. We've been working with them for about 4 years now.
I see. And in what kind of applications do they use this? Are you
Well,
allowed to say?
they're making Josephson junctions. That's commonly known for their superconducting quantum computers.
Oh, I see. No, but I mean because resistance, you have them like in any other chip other than quantum chips. So in principle, you can
Yes,
approximate. Yeah.
yeah. So we can work with these various different materials to give one of the difficult things with these materials is the characterization. To understand the materials and the characterizations of these things are very challenging. We're fortunate that we have access to the University of Alberta NanoFab. And so we can go there, we can look at things, we can test things, we can measure things, but not one organization has everything. So we have to go all over Canada sometimes to actually get measurements to understand what the dielectric constants are, what the thermal conductivity is, what the impact strength of these materials are, and of these coatings, etc., to hermetically seal chips and things like that.
Okay. Thank you.
Just to follow up on that, what are some of your Canadian partners, if you're allowed to share, who are helping with those measurements and devices? And
Oh, 1 second.
oh,
to put it
We
on this.
had the batteries.
Yeah.
It's all good.
Oh, okay. What are we allowed to share?
Sorry, yeah, no worries. I just wanted to follow up quickly before we go back to Lorna, about the Canadian collaborators that you have. If you're allowed to share any of who you work with to do those
Well, we
measurements.
work with different universities. Like we work with professors at the University of Alberta, University of Calgary, University of Ottawa. We're trying to work with University of Victoria now. Um, and we work with a number of different researchers in each of these different universities. It depends on the problem.
Yeah, so do you find that the devices to do those very precise measurements and classifications that you have to do for your materials, do you find that it's not really the industry yet that you're reaching out to collaborate? It's still the research labs?
Yes.
Yeah.
Because the materials are very novel, and as a result, we have to find the appropriate partnerships to work with, that they have equipment, devices that or systems that we need to test things on. As a company, we cannot afford to have all of this in under one roof. So we have to use what's available to us.
Yeah, definitely. Awesome. Thank you. Back to you, Lorna.
Dr. Antonek, I have Rael. He has a two-part question. One, he's asking for you to clarify again the meaning of the acronym HSQ.
Yes.
And then if you are able to comment on the working lifetime of any of the functionalized surfaces or products that you make.
So, HSQ stands for hydrogen silsesquioxane, which is a cage or ladder molecule that has silicon, hydrogen, and oxygen. It's a little cage molecule. And we can control the manufacturing of that molecule down to about 3 nanometers. And we use those materials for creating a photoresist. So it is the materials are susceptible to energetic beams. And using energetic beams, whether electrons, ions, photons, etc., the materials will change. They will cross-link. Or now we're developing ones that it will fall apart to reverse. So it's reverse applications. So instead of building the patterns, we can actually take away the patterns and leave what's left over. So the versatility of these materials, and it's all about chemistry. It's all about manipulating the molecules on the in this cage molecule and other things like that, taking off one molecule, putting something else on. So the second question was about usability. Some of the coatings and things like that that we're doing are quite permanent. They're like permanent glass. It's not going away ever. In some cases, these coatings will be used in a typical consumer environment, and as a result, we're still doing testing on some of the clothing, on some of the other coatings, etc., to see how long they will last in normal wear and tear. I mean, nothing will last forever on a coating. It just comes right off but the idea is to make it durable so that you can wash it 20 times and the coating is still there.
Thank you. Let me see here. Oh, Monica. Monica has a question. Which sectors have the biggest use of quantum materials? What is the market saturation?
Ooh, I don't think there is anything such as a market saturation for these things. I mean, we simply get more and more applications coming to us. And it doesn't seem to have, I will have in my inbox a weekly, somebody is emailing us weekly about some application. And we have some very creative staff. So we pose the question, can we do this? Or this company wants to do this. I got one out of Finland the other day, which is like, okay, this is really blowing. They want to do this with us. This is a multi-year development project, but if it works, I mean, you've got Harry Potter clothing or whatever, invisibility stuff. I mean, but
Whoa.
understanding the materials, you can create these things by combining, different polymers, different other nanomaterials to create something that is something completely novel.
Wow, that is amazing.
Thank you. Yeah.
Yeah, Monica, did you have any follow-up? Did you want to ask? Oh, you're up.
Well, well, so many industries, but how that looks in the public services is like, I believe the private companies, they might be more kind of tailor-made, customized, but through the application to citizens, maybe some kind of more standardized flow or some more wider application somewhere.
So, I mean, you're using, if your quantum.tv uses quantum materials,
Okay, I'm going to share my screen with you
your
here.
screen on your cell phone uses advanced materials.
Let's see.
But the problem with your cell phone is that you've got these fingerprint oils that are always mucking up your screen, and you're always cleaning your screen. So we developed a coating. Now we put it on polymer, we put it on glass. It doesn't have any residual oils on it. Now, how long that will last, we don't know yet. We're still working on the testing of it. But I mean, I got some beautiful videos of dragging oil all over the top of a piece of glass, and it doesn't stick.
Wow, that's really
So
practical.
Yeah, that's a practical application of a problem that can be used for a cell phone display. But another one that came out recently is microfluidic chips. So when you're putting in cells, blood, etc., into the chips, there's a stickiness, and you have these chambers where the cells, the fluids go through. Well, they stick to the sides of the chambers. So with this coating, we can actually coat it and nothing will stick to it. And then everything will flow through properly. Your microfluidic device will operate as intended.
All right. Thank you.
Wow. Amazing. I think Marco had his hand up and then it disappeared. Did you want to ask a question and then we'll go to Yanis?
No, let's go to Yanis.
Okay. Yanis.
I disagree. We should go with Marco first. Go ahead.
Okay, cool. Yeah, I was thinking about this, like the development that you talked, that every time you have like new projects, new applications, like what about on the theory side? Do you have like your eye on specific materials that that are like being developed, being studied, like for example, spin liquids that you say, oh, if they develop this, then we have like this application.
Most of the time we're playing catch up all the time with regards to materials development because people want things already. But in terms of like developing new things, I think the area that we're exploring the most is these various different types of polymers that have material functionality to it, so that we can actually create, by creating the material and having it interact with the various different energy source, where it's a light or laser or beam of something, to actually have it do what we want. There's where the real interesting challenge is. And people ask us, do we use AI for any of this stuff? And the answer is not really, because it hasn't been invented yet. So AI wouldn't have a clue of exactly how to figure it out. So that's a bit of a challenge, but we do use a little bit in terms of posing a question. What if we did this? How would that work? And sometimes we get some very strange answers, but a lot of times it's just faster to say, set up 6 reactions, run it, and see what happens. In a day, we'll have an answer.
Mm-hmm. I see. Thank you.
Go ahead, Giannis.
Okay, so thanks very much for this presentation. I won't pretend that I understood everything because my background isn't so much into the nitty-gritty of all this. But I do have a question so it seems to me from what you've been saying is that it doesn't sound like you have many limits in terms of the applicability and your attempts to try to figure this out, with all these things out, which is really impressive. And there's so many applications that it's kind of mind-boggling how I wonder. So you said you have very creative people. I also wonder how you keep track of all the possibilities. You must have extremely intelligent people, not just creative. Well, both, I guess, is at the same time. But my question now is to what ethical limits you have as to what you do and don't do. Because you just mentioned that there's people out there who are working on making invisibility. And that can go really, really well for, I guess, I'm not sure, but then that could also go really, really badly, depending on what they're making. So yeah, I'm wondering as a company, what's that, what limits you? What do you refuse to do, let's say?
Well, sometimes our clients don't tell us what they want or what they're doing. That's the unfortunate part. So we can sometimes figure it out because we can go into the background of the researcher and say, what's his background? What has he been working on? Boeing one was an interesting example. The researcher, he was buying our materials. His expertise is in adhesives and glues. So I said, okay, adhesives and glues, whatever. I mean, that's not dangerous or anything like that. It's just that. So, build a better aircraft or something like that. That's great. Or space shuttle or probe or something like that. So we do sort of understand a little bit about what the application is. We try to, anyways, at least, especially if we're getting into some joint development. We'll know very quickly what we're working on. So in terms of limitations, you talked about environmental or ethics and things like that. Our materials are primarily biocompatible materials. They're all silicon. So primarily silicon, silica, silicones, etc. Some irons, other things like that we work with. Carbons and things like that. They're not hazardous materials. We make them sometimes can be hazardous, but primarily the materials are benign. I mean, we're injecting these materials into mice. We're putting these materials onto skin. They're benign materials. The body uses silicon. It represents a couple of grams in your body. Your hair, your nails, your bones use silicon. It's a necessary element in people's bodies. People don't realize that your cake mixes, your beer, your plastic wrap, all have silica in them, and we're ingesting it. Your toothpaste has silica, so I mean it's a natural material, and it's what the most common element on the planet, sort of thing, other than oxygen, I guess. So it's very useful, and we don't. There was one project that a company proposed to us, and we did this for Health Canada. So it was lead nanoparticles from exhaust, from cars, from other things like that. There was no source of lead nanoparticles that they could procure. So we actually made them and then sent them for testing. I mean, it was for a health-related thing. I mean, it's a toxic material, but it was for health research.
You
So
had to
that's the sort
create
of
it
stuff that we'll
for
do.
them to test it. Yeah.
Well, and so sometimes the best way to know what is dangerous or not is to actually test it. So
Yeah.
it's and then I'm not at all trying to find, blame for that. It's just that sometimes would you say that when you find out that a project is distasteful, we'll say ethically, do you halt that partnership, or do you that's kind of the question that I have.
I don't really, I don't think we've ever gotten there to that stage with anybody yet. I mean, we have in the past dealt with some unethical companies, yes, and we just stop. We just say, thank you very much, and we're not going to work with you anymore. I mean, these are companies that are trying to steal our technology, etc.
Oh, okay.
Oh
Yeah,
yeah.
that's
Oh yeah.
more of the
It's
concern.
it's a ruthless business world out there.
That's interesting to know, because you are making some very cool stuff, and not just cool because of the science, but because of the applications. And I could in the back of my head, and maybe everybody else here was thinking, well, this is stuff that I'm sure gets stolen or attempts to be stolen. So,
Mhm.
hmm.
So yeah, so that's one of the areas that we're very cautious on is intellectual property protection, trade secrets,
Hmm.
cybersecurity, all of that sort of stuff.
Thank you.
Yeah, great questions, Giannis.
Thank you for that. I have Monica with a question, and then I see Mariana with her hand up after. Monica's question is, what is the most unique properties your company has delivered in response to client needs?
I think the amphiphobia one is the most unique because nobody has done this before with PFAS-free materials. We were in April, we were at the big German textile fair, 1,700 exhibitors. This was our first time there. And we were, a new small company way in the back. We were overwhelmed with inquiries. The word got out through um, the trade show directory and through word of mouth. We had 76 meetings in 4 days. It was insane because we had something nobody else had. And that has led to right now, I think we're 8 or 9 projects that are currently getting started just because of that one trade exhibition. I mean, to have an amphiphobia coating that is completely safe, biosafe, it's really touched a lot of people and companies.
I think that shows how important it is for all this collaboration that happens, right?
Yep.
All of the things that come out naturally from that. That's amazing to hear. Mariana, feel free to unmute your mic.
Thank you. Well, this has been fascinating. So thank you so much for the whole presentation and for what you are doing. And hope I can pay you a visit at some point. And I'll tell you about my story. I have been around for a long time, and I started working with thick film hybrid circuits in a lab like 35, 40 years ago. My question is, this all seems, really, real materials. We are talking about real things. And I'm curious about, where do you stand in artificial intelligence? How do you use AI? And because somehow your materials or all this technology is going to be the base, the quantum computing for whatever we are going to do, or the world is going to develop artificially. But I would like to hear from you, where do you stand with all that?
So we use it internally. I mean, for searches, for understanding markets, looking at what the competitors are doing, trying to figure out, okay, what is this application, what the impact of this application is going to be, like the social stuff. But in terms of the hard science, that's still done by smart people, PhDs, masters, engineers, chemists, and nanobiochemists working in the lab. There's no substitute for that. You need to be in the lab, playing with the materials, working on the in the lab, making something and then testing it out. And then you can verify that and say, okay, I made this, does it work? And then we publish a paper, or we publish a presentation in a conference, and guess what? AI will now say, oh yeah, there's this new technology, because it's meta crawling out there, is grabbing information that's already done. But because we've never done it before, there's no way it's going to figure this out. I mean, it can speculate and other things like that. There's examples of it. It does that, but there's no substitute for the actual work in the lab.
Thank you. Thank you so much.
Are there any other questions from the group? Feel free to type it, or by all means, just unmute your mic. The floor is yours.
So I did have one that I would like to understand. What is the difference between quantum materials and nanomaterials?
Well, I guess nanomaterials are just small materials. Quantum has a quantum effect. As you know, there's a quantum effect that's going on with that. There's in our cases, we bridge the gap between both.
Makes sense. Thank you. So quantum is the effect. So it's the nanomaterial that is quantum susceptible,
Yes.
kind of. Yeah, thank you.
Wonderful. Great questions. Yeah, love all the engagement. Marco, do you have any more? I know you might have a couple burning, no? Okay. All right. Lorna, do you see?
Oh, there's one more that just popped up here.
Yeah.
Monica's asking, which property is hardest to preserve outside of the laboratory?
Shelf life sometimes. You have some of our materials are, I mean, they react to the environment. So light, heat, cold, that sort of stuff like that. So the materials are sometimes ultra sensitive. So shelf life is a key component of developing the materials, so that and storing it, handling it. That's a whole another problems that we face when we ship products all over the world, and it has to arrive in pristine conditions and stuff like that. So we seal stuff in vacuum. We do all kinds of creative shipping to get the product to the customer.
Thank you. Marco.
Yes, couldn't resist. When you build the quantum chips, they usually are like in a flat sheet. But I've seen that if you allow it for it to be like on a third dimension, so if you have a cube of qubits, then you can do like very good quantum error correcting codes. Is that something that someone has approached to you on starting doing,
No,
or not yet?
not yet. No, we're not really into the processing and the software side of it. That's usually somebody else's job. I mean, we can't be doing everything. In terms of the idea is to build the materials with minimal defects, highest purity, complete stability, so that it's usable in a practical application.
I see, but like for instance, like when somebody is trying to build a quantum chip, is it you that builds like completely the chip and then delivers it?
No, they design it. We make the materials for their design.
Oh, and they ensemble it.
Yeah. So actually,
Okay.
in a couple of weeks, we're going to be working, having a meeting with I guess you could call it a chip design company. So they want to understand how our materials can affect new chip design,
I see.
which is going to sort of get to where you're what you're thinking.
Hmm.
And maybe that will get us into, that particular area.
I see. Thank you.
Yeah, it's so fascinating to see how all the pieces, as you know, like I'm sitting in different sessions and hearing different speakers. So it's like putting a puzzle together and like seeing the flow of how something comes from the materials into what it can do. So it's really fascinating to hear your side of things.
It's literally the foundation.
Literally. Okay,
Yeah.
Giannis, feel free to unmute your mic.
Please let me know if there's no time. But yeah, I have I guess a supply chain and materials question maybe.
Oh, that's a
Uh,
good one.
where do you get your materials from? Yeah.
Okay, so basically we get raw chemicals.
Okay.
So that comes from various chemical suppliers, whether they're in Canada or US. We get things like ethanol and toluene and various just other exotic chemicals and stuff like that. It comes from various different suppliers. We take those raw chemicals and then we process them, make something out of it, and make these nano and quantum materials out of these raw chemicals. So we do it from ground up.
Hmm.
So there's the bottom up and top down. We go from bottom up.
I guess the question also comes from because when I hear the word materials, for some reason, and then you were talking about metals, so I think ore in my X minor supply chain brain. I think of ores, and now you're saying chemicals. So I'm guessing somebody else is grinding all those things up and putting them into liquid form that you then use.
Pretty much liquids or powders and things like that.
Powders.
I mean, we're getting ourselves, we're getting into a little bit, thought of making our own chemicals from scratch. That's another area. Depends on volume, depends on need. There's been changes in the industry. In the supply chains, there's been some breakages in the supply chain. So we may have to start making some of our own precursors and chemicals ourselves.
Yeah, and I'm guessing with what's going on concurrently with the economic environment that we have, there might be some changes to the prices.
Hmm.
Hmm.
Yes, and so as a result, we have to adapt.
And would you think so? I guess a follow-up question to that is, sorry, Simon, uh, is uh, do you think it would be cheaper for you to make it in-house?
Probably not at scale. I mean, if it's a specialty material that is small enough, yeah, we could probably do it cheaper. But if it's a bulk commodity, no, we still have to outsource it from somewhere else. I mean, these companies that make toluene, I mean, they make it on the million, liter scale sort of thing. You can't compete with that. So it's cheaper to buy it.
Okay. And you said it was mostly the United States and can I guess
Yeah.
local the
No,
suppliers that you
there's nothing local.
nothing local?
No, nothing local that I'm aware of. Most of the stuff comes from foreign uh, suppliers and stuff like that. And I mean, it's a problem. I mean, Canada doesn't manufacture much anymore. And as a result, we're dependent on foreign nations for even the basic materials.
Okay, wow. That so that's another challenge that I'm sure you
Mhm.
have in that list of challenges.
Yep.
Huh. And are there, I guess, sorry, Simon, I'll stop asking questions. But I have one more follow-up question because of that, because it's so interesting. Is Canada doing anything about that? Do you know if the government of Canada is pushing for anything to happen?
Not that I'm aware of. I mean, they have a critical mineral strategy, and so they're investing in critical minerals and things like that, mostly for rare earths and graphites and batteries and stuff like that. That's about the only strategy that I've seen.
Hmm.
The Canadian quantum strategy is flawed. I mean, they're barely even considering, advanced materials as part of their pillars for communications and computing and sensing. I mean, I've been advocating this for years now, that the quantum materials are the foundation for building any device. And without it, they're finally starting to get the message.
Okay, so there's some good
Yes.
coming out of this,
I
right?
think they're finally starting to do that, and part of it is a lot of interacting with the right people in governments and things like that. There's all kinds of, we don't have to do things the same way, the old way.
Mhm.
There's all kinds of creative new ways of making better, faster, cheaper, etc. And sometimes, government just get in the way, really, of some of these things. Their policies are just problematic.
So that's very interesting for you to say. I think this is the first time that I've heard somebody of you, I guess, an entrepreneur of your stature will say openly criticize the quantum plan that the government has.
See, the policymakers, they're not in industry. They don't see what's going on. I mean, there was one I met in Germany under the Silicon Saxony. Policy people, they stay in their office. They don't go out. They don't see what's going on. They go to a trade show and they see what's going on, a few things like that. And they go, okay, well, that's interesting. And I challenge them. I say, okay, in your policy development, did you ever talk to industry? Oh, well, yeah, we had some consultants that talked to somebody or something like that. I said, do you really talk to industry to know what's really going on? To understand, like, we see things before anybody else because people are trying to develop something new, and then they have to come to us to say, can you make this material?
Okay. No, thanks. This is great. I mean, typically a question that I've been asking, Katanya knows this, is that I've been asking other entrepreneurs that have been invited if they feel that their work is understood by people and government outside of the industry, we'll say.
Emphatically, no.
Okay.
However, that is part of the motivation for having these webinars.
Exactly.
There's a whole new webinar for you.
Yeah, no, but that's great. I would be very interested in that kind of webinar, but it's the kind of social kind of grasp of quantum tech and quantum materials, I think would be a very interesting place. I mean, you could invite all sorts of entrepreneurs and specialists to come in and I want to hear what they have to say and not just what people think of quantum, because it doesn't seem
a round table.
Yeah, exactly.
So, and invite various speakers, yeah.
But sorry, thanks so much, David. Let Simon take over if he has a question.
Yeah, please. Let's have one more question from Simon, and then we'll finish off our webinar. And then if you want to stay on for a little bit more, we can do a couple more Q&A off the record. So, to you, Simon.
Thanks, Katanya, and thanks, David, for your presentation. And Yanis, you were asking a lot of questions that were similar to what I'm interested in too, about supply chain sensibility. And I know that, David, you mentioned some of the environmental considerations that new materials can address. And I'm curious that from an industry perspective, if you've also heard about like indigenous rights in relation to either material extraction or downstream impact, and if that's a consideration that is present in industry developments and in understanding like the land base and the rights and title that the quantum infrastructure is being developed on top of.
Okay, I can get into a whole nother rabbit hole on this one. All right, so AQM spun off a second company called Dark Matter Materials. Okay, Dark Matter Materials is a company that is addressing the the problems that we're having in the energy sector, okay, with dirty water, cleanup, tailings ponds, frack water, whatever. So we are our dark matter materials has been developing processes and nanocatalysts. So these again are the nanomaterials that are being used to clean up wastewater. What I found was that we have governments, provincial, federal, indigenous groups, municipalities, all arguing over how to do this. And I said to them, look, just do it. Just start with something. You're not going to get it perfect the first time. And he says, companies asking us to remove organics or certain oils and acids in the tailings pond water. We've demonstrated we can do it. Now the question is scaling it up and making this technology available. The problem is everybody wants zero. They want nothing. And it says, well, you can't get it nothing on the first try. But if you can get 90%, do it. It's a big improvement over what you got now. So in time, you'll get 94%, 96%, and then you'll eventually get 100% removal of some of these materials. But you have to start with something, and you can't keep arguing amongst themselves about what the lower limits are. So yeah, that's a whole nother area. But we have been working with indigenous groups to kind of explain to them that this is what the reality is. Science it evolves. It takes time to find the complete solutions. But you start with something that works now, and then you continue evolving it until you have the all the answers.
All right, thank you.
Yeah, wonderful questions. Thank you. And thank you very much, David.
It looks like we have a few more, but like what Dr. Katanya said, we're going to kind of close off on this webinar first, and then we can continue with some other questions. Dr. Antonuk, I just wanted to add that Giannis, I think Dr. Katanya will agree with me, is probably single-handedly the reason why you are here, because he has been one of our most active participants in Qubo webinars and has shown great interest in materials. And so Dr. Katanya went on it and found this. And so it's so cool to see how one webinar can beget the next one and so on and so forth. And how grateful and how lucky we are to have Dr. Katanya make this stuff happen. So thank you to Giannis. And thank you to Dr. Katanya for making this. And yeah, like your suggestions of a roundtable and stuff, like I said, the meeting of the minds of everybody. And that goes to everyone that's here as participants, right? You show where your interest is. That gives us a good temperature reading on what everybody wants to hear.
Exactly. Yeah, I echo everything Lorna just said. Well said.
Don't do this to me.
Giannis, you've already been nominated as a moderator for a panel.
You've got the guest. Say this to the guest.
Oh, it's a team effort. We want the guests to be also able to be themselves, and clearly this interaction has been very good.
It's very. I think it's very useful. There's a lot that I learn about this that's quite shocking to me. The fact that Canada is I feel like Canadians don't often understand how it's not just that they're lucky to have what they have, but that there's so much creativity and there's so much activity going on that we don't necessarily hear about. It's not necessarily publicized. Maybe you want that publicized, maybe you don't, it depends. But there's also, so it seems to me that conversations are not occurring, and that's the most shocking aspect of it. The government has these desires, these goals that they want to achieve, and they have the people right next door. But that they're not talking to these people is just mind-boggling to me. So in a sense, I almost want to say Qubo is you're as a consulting corporation, like you're you're doing the great work, but I think you should also potentially be the middle person, not just for people, individual Canadians, but also potentially policymakers, because
Yeah, for sure.
it's
I do have some policymakers on my client list. Don't worry.
yeah, and if they could, I hope they're listening, because this is important stuff.
I 100% agree. And yes, thank you very much, Yanis. I want to continue our conversation. I just want to finish off the webinar recorded session. Thank you again to our guest speaker. You were wonderful, David. That was fantastic. I loved all the engagement. I think your content hit right on the mark. So we hope we can have you again.
Well, I hope everybody enjoyed it, and it was fun and very interactive, and you got a great webinar going on here.
Awesome. Well, we're gonna keep her going. Don't you worry.
Yeah, I'm gonna start, telling more people about it.
Aw, thank you. We appreciate it. And everyone that's attending live right now, you're going to receive both my slides as well as David's slides, and also a certificate of attendance. And please spread the word about these webinars, post on your socials, connect with me on LinkedIn. Soon Qubo is going to have some more social accounts rolling out this summer. So lots of ways to keep in touch. And in case you're interested in some formal training, perhaps your work already sponsors training for your job. I have some cohorts starting in September. My partnership with NAIT, the Northern Alberta Institute of Technology, these are all online quantum courses. There's 2 certificates. One is for executives. It's non-technical introductions. Each course is only 1 hour. And then there's the Quantum for Engineers certificate, which is a more technical course. They are 2-hour courses. And I can also offer you a discount code if you contact me. So please check it out on the website, quboquantum.com. Scan the QR code. Go to the NAIT website. It's also there. And I hope to see you at another future webinar or course. So thank you so much.